All right, let's try to read that again. And so the glomerular filtration is the first step in urine formation, followed by reabsorption, secretion, and water conservation. Whatever comes out of the glomerulus is passed on in the capsular space. This is similar to blood plasma, except that it has no proteins because protein is kept back in the tubules, in the small arterioles. So remember that from this picture here, we bring it back here. All right, there it is. The afferent arteriole has branched into many smaller arterioles, and in that smaller arterioles, all of them have these slits or opening. So as you put pressure through this, you will filter out the ions or the items that need to be taken out of the blood, and they will fill this capsular space. They will all be collected and drained into this tubule. So remember that, huh? This is like the main filtering mechanism of the glomerulus. Blood is pressured in, and then it's forced. The filtrate is forced out through the slits, and then is collected in the capsular space, right? Still inside the glomerulus, and then filtered out. Okay. Having that idea, the glomerular filtrate is the fluid that we said was in the capsular space. This filtrate is similar to blood plasma, except that it has no protein because the protein is not supposed to go through the filtration slits. It's too big and therefore stays behind. Substances that have been removed or added to the tubular fluid will be processed all the way to the distal convoluted. So there may be some other substances that will be secreted. It will join the tubule. Finally enters the collecting duct and will be pushed on to the minor calyx, major calyx, and out into the ureter. Like I said, these are examples of the glomerulus. You can see the filtration slit. They're really small, and the red blood cell is not supposed to make it through there. There's another picture here. So this is the actual arterioles. Remember the afferent arteriole break into some more smaller arterioles. So this is one of the smaller arterioles, and the red blood cell and blood is passing through them. But through these arterioles, you will have these slits, this filtration pore we call it. Okay, filtration pore on this side, but slits on the basement membrane side. So basically, all these items, all these items, water, electrolyte, glucose, all the way to creatinine, can be filtered out. Because of the pressure, it will be pushed out and into the capsular space, right? So that's allowed to go through. The blood cells, this red blood cell right here, will not make it through because that's too small. And that's also a good thing because then you don't bleed into the kidney. You don't release blood or lose blood, almost like you're bleeding. So this is not let out, and basically plasma is the one, a plasma-like filtrate is the one that results from this filtration. The proteins are also not let out. They're also big, and large anions, protein-bound minerals and hormones. Some molecules that are big are not let out. But now what happens is, in case for if the pressure is too strong, it can force these openings to become bigger. And when that becomes big enough for the red blood cell to pass through, they lose red blood cell. You have hematuria or bleeding in the urine. And also, if this has been opened wide or forced to become destroyed or made wider, the proteins will also flow. And if you lose a protein, you'll have proteinuria, Um, and lack of protein in the blood vessel will make you not be able to pull back water to stay in the blood circulatory system. So this is dangerous if it becomes bigger. In fact, it will lead to renal failure. Okay, it's not supposed to be big. Another item is if you have an antigen being captured by the antibody. So that complex, antigen antibody complex, can end up irritating this area and end up in an inflammation. Okay. For example, you have a condition where a child had streptococcal sore throat, and this is group A, huh? Group B is in the genitals. So he had a strep throat, and if it was not well handled or managed, your immune system will make an antigen antibody, right? Your antibodies will um, capture the antigen and stick to it. Now, this will form an antigen antibody complex still in the blood. When this flows in the blood and it just those filtration slits, okay, then it can start an inflammation there, right? It's trying to get through, but it's not making it through. It may cause inflammation there. And inflammation, it starts there, you will have what they call glomerulonephritis, inflammation of the glomerulus and the nephron, the whole tubules. This is basically called PSGN. That's another word, the abbreviation. PSGN, post streptococcal glomerulonephritis. If this happens in a child, you will see the child having high blood pressure and also having puffy cheeks, like a edematous, and very ill, huh? So if you can remedy this, then you will be able to lessen the situation, the blood pressure, fever, and all that. And this is because of the antigen antibody complex that irritated the lining or the inner surface of these smaller arterioles. Huh? Okay, that's just one example. Any other item that irritates the surface can cause inflammation, and if there's inflammation, it can also cause scarring, right? Huh? Where it will not function anymore. All right, so it can be either destroyed, become bigger, or scar, and it's not functioning anymore. So how would it be able to filter? All right, huh? So the filtration membrane are barriers to which the fluid passes. We call it fenestrated, like we mentioned in the beginning of a chapter. You'll have a basement membrane, filtration slits. Huh? Albumin is repelled by negative charge from the basement membrane. Blood plasma is 7% protein. The filtrate is all about 0.03% protein. Like we said, small protein. That's not even needed. So the bigger proteins they say inside the blood vessels. This is also all throughout the arterioles that we mentioned, so effectively doing filtration work. So the size matters, huh? Anything that is smaller than 3 nanometers can pass through. These are items that are close to that size. Some substances of low molecular weight are bound to plasma proteins and they will not make it through. Okay? The kidney infection and trauma can damage the filtration membrane, like we mentioned, and therefore change the limiting factor or limiting ability of that membrane. This is basically what we described. Distance runners and swimmers often experience temporary proteinuria hematuria because of the strength of pressure perfusing the kidney, and sometimes it forces red blood cell and protein through the slits. Glomerulus deteriorates if there is too much hypoxia time exposed to the glomerulus. Right? It can be damaged by prolonged hypoxia. Now, this mechanism of filtering in the glomerulus depends on three factors. That's blood hydrostatic pressure, uh, pressure in the actual uh, fluid or blood, which is the osmotic pressure, and pressure outside of that glomerulus. So when we look at it, okay, take a few minutes, a few seconds to look at that. This is the glomerulus still, and this is the afferent breaking into many arterioles, and this is where it comes out the efferent. Okay, so check that out for seconds. Right now, if you do the math, the blood hydrostatic pressure, which is basically the pressure from the heart, is about 60 millimeter mercury. The colloid osmotic pressure, which is the proteins in the blood trying to keep the filtrate or the plasma-like filtrate still inside the tubule, is about 32. The capsular pressure, pressure from the fluid that's already outside here, trying to force or prevent anything from coming out, is about 18 millimeter mercury. So the numbers say that you are 10 millimeter mercury dominantly pushing fluid out. The blood hydrostatic pressure defeats the both other countering pressures. But basically, what happens is by these forces, you actually lessen the pressure coming from the heart, which is good, huh? Which is good. I'm glad we have the colloid osmotic and the capsular pressure, because by decreasing the pressure, we have a nice flow of 10 millimeter mercury. It will not damage the filtration or the pores that it passes through. If it's just too big, meaning too strong, let's say you have a protein, and therefore your colloid osmotic pressure will decrease even by all the way to 10, for example. Then imagine how stronger this pressure will be. Okay, yeah, if this was at 10, you would end up with 22 millimeter mercury pushing against the walls of those arterioles. They may break. At a good enough pressure, they may open the filtration pore and slit and damage the whole kidney. So again, too much pressure is also not good. Let's say you have good enough protein, your colloid osmotic pressure is good. Pressure in the capsule is also good. But if you have too much pressure coming from the heart, like in a heart that's over pumping, then it will also make the 60 millimeter mercury a bigger number. Let's say 70 or say 5 or 80. Therefore, you have renal hypertension and will also develop a lot of pressure in the system. Okay, that can also definitely damage the glomerulus. Now, what happens on the other end in case the 60 millimeter mercury is not met and it's only pushing a weak 40 or maybe less? This happens in congestive heart failure or any restriction in the artery. So, less pressure inside. What would happen is if the pressure is not enough to push filtrates out through the slits, it's not enough pressure to push the filtrate out of the slits, then you will end up not cleaning the blood. The blood that enters, okay, the blood that enters here is so weak in pressure that it's not even able to push out the filtrate. These other pressures, colloid osmotic pressure and capsular pressure, defeats it. So the filtrate or the waste will not leave the flow. In fact, it will stay there. It will still come out of the efferent, still unclean. All right. When that happens, then you will build up and lead into a condition such as azotemia. All right, because the waste is accumulating. So low pressure will be a problem too. High pressure will also be a problem. You got to be at the right level, which is not really a narrow margin. It's pretty wide level to avoid the disease. Okay, so keep that in mind. Basically, this is what is described here. I'm going to skip it. Okay, there's two, and the same thing here, huh? All right, the GFR is controlled by the glomerular blood pressure from moment to moment, and this is maintained by renal autoregulation, sympathetic, and hormonal control. Let's go to renal autoregulation, the ability of the nephrons to adjust their own blood flow, and GFR without external or hormonal control. It helps the kidney maintain a relative stable GFR. GFR means glomerular filtration rate. Glomerular filtration rate. um, Two methods of autoregulation. We call it myogenic mechanism and tubuloglomerular feedback. All right, we have here the myogenic mechanism. So if the artery blood pressure increases, the afferent arteriole stretches, and the afferent arteriole constricts to prevent too much blood flow in the glomerulus. If the pressure is low, then you expect it to dilate or let go of the afferent. Okay, so let's go back to the picture so we can better explain this. Let's see if there's a picture here. Uh, okay, let me. Okay, here's your afferent, afferent arteriole. This is your efferent, and that's the glomerulus where the blood went in. If the pressure is too high, this will constrict because it doesn't want it to get the glomerulus damaged. For example, you are in a sympathetic, parasympathetic mode. In sympathetic mode, where the pressure is high, you don't want that pressure to damage this glomerulus, so the afferent will constrict a little bit. Okay, and if the pressure is low, then you need to open up, and the afferent will dilate in order to allow more blood to go through. Otherwise, you will not have a renal function. Sometimes when the pressure is really low, wide the afferent goes, and the efferent actually constricts. So you can imagine you trap the blood inside by opening wide on the afferent, but you trap it and close on the efferent, so you have a lot of blood in the glomerulus. This will increase the pressure enough to filtration. So all this mechanism is happening because of the changes in the blood pressure. All right, so the afferent arteriole can constrict or dilate depending on the situation. And its main effort is to protect the glomerulus. All right, now let's get back here. If the glomerular filtration rate increases, more sodium chloride is reabsorbed and more adenosine is produced locally. Adenosine stimulates the JG cells to contract to constrict the afferent, reducing GFR to normal. So that's another side effect of adenosine. The If there's too much perfusion, it will stimulate the JG cells to contract, controlling the afferent. Okay. If GFR falls down regular levels, the macula relaxes the afferent arteriole, and then blood flow is increased and GFR is brought back to normal. Okay, so in case again, another method of GF to increase GFR is to constrict the efferent, and therefore trapping the afferent and increasing pressure in the area. Okay. The granular cells also contain granules of renin, which they secrete when you are needing to increase blood pressure. All right. Now let's go ahead and enter the next method, which is involving the juxtaglomerular apparatus. Okay, the JG cells or juxtaglomerular apparatus is actually this mechanism here. Remember when I told you that it's significant why the ascending tubule touches in close contact to the afferent and the efferent. See how they are when this tubule is close to this area, especially the uh, afferent arteriole. So what we can say is if there is too much pressure coming from, and by the way, let's identify first the parts here. This is the macula densa on the efferent tubule, and then this is your granular cells. Okay, and then you have the afferent, and then the efferent arteriole. The granular cells here contain the JG cells, juxtaglomerular items or cell. Right. Okay, so one idea here is there's too much pressure passing through the tubule. High GFR, increase sodium will increase sodium chloride loop in the nephron. Macula densa secretes ATP, which is the energy, and mesenchymal cells metabolize ATP to adenosine, and adenosine stimulates the granule cells, which opens up the passage towards the afferent arteriole. Therefore, you will reduce your GFR. Okay, that's another mechanism, the tubulo-glomerular feedback. Again, the idea is here, in case the tubule is experiencing low levels, it will alert the JG cells, right? JG cells found in that uh, granular area. The JG cells, when this happens, the JG cells will um, constrict the afferent. Again, if there's too much filtrate passing through the tubule, it will tell the JG cells to constrict, and the JG cells will constrict the afferent. Constricting the afferent leads to less blood coming in, and therefore the pressure is decreased. Okay, so again, if on the other hand, if this tubule experiences low flow, the mesenchymal cells will also detect it and then send a signal through the JG cells to open up so we can get more blood in. So it's like a good system that everybody cooperates. And that will be right at that junction right there. Right? We call it the juxtaglomerular apparatus. And that's a tubulo-glomerular feedback as well. All right, sympathetic wise, right? Sympathetic nervous system, adrenal epinephrine will constrict the afferent. Why? Because by constricting the afferent, you lessen the flow inside the glomerulus. When you have less flow in the glomerulus, that means your urine output will be less. In a sympathetic drive, you probably don't want yourself peeing a lot. Doesn't make sense, So what it does is it can do many ways. Number one, it can do constriction of the afferent and therefore reducing filtration rate and output. It also redirect blood from the kidney back to the heart and brain even and skeletal muscle. That's the parts who really need the blood flow. Also, there's a renin-angiotensin-aldosterone mechanism that helps control the pressure and filtration rate. When you have a drop in blood pressure, the baroreceptors in the carotid aorta stimulate sympathetic nervous. The sympathetic fibers trigger release of renin, and therefore also makes the renin comply. Okay, so because of that, renin can be able to convert angiotensinogen to angiotensin 1, which is leading to promoting the release of antidiuretic hormone. and also general increase in water. Okay, that leads to your RAAM, and we'll have a special slide on that later on. Actually, it's over here. Let me make sure we don't have this. Huh? Okay, let me show you this. All right, this is your RAAM, renin angiotensin aldosterone mechanism. Okay, so to begin with, the kidney has experienced a low volume, low pressure. Okay, and the G cells will do is it will release renin. Renin will convert angiotensinogen coming from the liver, convert it to angiotensinogen 1. Oh, I'm sorry, angiotensin 1. Now, angiotensin 1 will be converted by the ACE coming from the lung, where ACE means angiotensin converting enzyme. You will have, after conversion from angio 1 to angio 2, angio 2 now can make three major steps. And everything else is supposed to be towards saving water, huh? Okay, so the first branch of angiotensin 2 goes to the brain, huh? It stimulates the brain, especially the hypothalamus, to feel the thirst, see how lack of water is happening in the blood or a little bit of a dehydration picture. So the area of the brain, the hypothalamus, will say, we need to release and connect this. Okay, we may release hormones, for example, your antidiuretic hormone, in order to conserve, conserve the water, and that will go to your kidneys to create aquaporins that will let water in. Now, another thing is when you stimulate the brain, by way of that mechanism, you actually make the brain stand up, make the body stand up and go for water. So that branch of the response is the actual moving to get water, because the brain felt the need to. The second branch is resulting in overall peripheral constriction, the smaller vessels towards the knee, towards the area where you don't need it in a parasympathetic mode. Then what happens is your flow will be constricted and therefore will help increase blood pressure. The third leg is when in the AP2 stimulates the adrenal cortex to release aldosterone. And by releasing aldosterone, you will end up saving sodium from the kidney, which is hopefully followed by water. So again, you're able to get the water we need. Okay, this is the renin angiotensin aldosterone mechanism. Very important. And practice, for example, knowing the products of the organ itself. Okay, for example, product of the kidney, renin. Product of the liver, erythropoietin. Product of the lungs, ACE, and so on and so forth. So that'd be a very useful tip. Now, if this is happening, let's go ahead and go clinical here. So you see what tensin can do, huh? And the next thing that would happen is, if this is working naturally, and for some reason the person still has high blood pressure, then we should look at all the possible causes and problems, or at least situations that can help the filtration. So if this is happening in a person with already high blood pressure, how can we not make this happen so we don't increase the blood pressure, which is the goal of this mechanism? So you're looking at inhibiting what enzyme, right? Inhibiting the enzyme that would produce angiotensin 2. So Basically, the lung produces the ASA, angiotensin converting enzyme. If we give a medication to stop, right, to stop the lungs from producing that, then we don't create the angiotensin 2. Okay, so to stop that, we may give the patient what we call ACE inhibitor. ACE inhibitor. So it will inhibit the enzyme or the hormone angiotensin converting enzyme from converting one into two. If you don't make a two, angio 2, then the three major responses will not happen. Okay, and that's your brain going for water, your vasoconstriction, and the aldosterone mechanism on the third leg. They will not end up producing the three items because you don't have enough HDL. And also, you don't have enough enzymes. So, by inhibiting the enzymes, ACE inhibitor, or by the ACE inhibitor, you will not create the rest of the angiotensin 2. Therefore, there's no further increase in blood pressure. So, in persons with blood pressure, we used to give, or what is, we're still giving ACE inhibitors, huh? And these are the enalapril, captopril, lisinopril, right? Almost all pril names. Therefore, it will block the ACE, and you will not be able to produce will not able to produce your angiotensin 2. Okay, now keep note, if you give the patient this ACE inhibitor and they complain of uh, stubborn coughing, non-productive, just suddenly after you started taking the medication, then that's an indication that this ACE inhibitor may not necessarily your best uh, medication because it's not able to do its function. Okay, so in a person who is already hypertensive, if you block the ACE, then you lessen the pressure making capability, and therefore it's good for hypertension. Huh? Another event that will happen there is if this patient does get irritating cough when he took this ACE inhibitor, then that means this lung is not able to survive the situation. We will have to discontinue the ACE inhibitor and make other ways. For example, maybe a change in the uh, actual diet, maybe, huh, to help offset the high blood pressure. And also maybe use other ways to decrease the blood pressure. For example, using beta blockers, right? Because we know ACE inhibitor doesn't work with the patient. Beta blockers and other uh, regimen that will help clear the situation. So ACE inhibitors, that's why captopril, lisinopril, right? Almost all the pril names. So be familiar with this mechanism. For example, renin is produced in a question that could be renin is produced by A, the lungs, the B, the kidney, I'm sorry, B, the kidney, and C is liver. So, the question is who produces renin? And your answer should be the kidney, huh? All right. Just a sample question there. Or it may be uh, the effect of angiotensin 2 is vasodilation to help increase the blood pressure. So right away you see there it's wrong because it should be right on the bottom, it should be vasoconstriction, not vasodilation. Vasodilation just gives you, puts you more in hypotension, and in the future lead to decremental changes in the body. Okay, if it's asked, where does aldosterone come from? A, the liver, B, the kidney, C, the lungs. Then you will always say it's coming from there's another choice, adrenal glands. So those four. Of them, the correct answer would be the adrenal glands, where aldosterone comes for. So see, a lot of questions can be derived from this, huh? So like I told you, I made you illustrate this because this will play a major role in your understanding, huh? Urinary system. Okay, take a few more seconds and before I switch over. All right. Let me. All right, let's move on. Basically, what we discussed here. Let's go for urinary tubular reabsorption and secretion. For here, this happens to the proximal convoluted to the distal convoluted. The steps involved is tubular reabsorption, tubular secretion, and water conservation. Okay, so again, our urine formation is the glomerulus filtration, tubular reabsorption and secretion, and then suddenly you have water conservation. All right, this is the effort on the internal part of the body. Huh? PCT absorbs a lot of the glomerular filtrate. Absorbs or reabsorbs means it brings it back to the circulation. Huh? Tubular reabsorption is the process of reclaiming water and solutes from the tubular fluid and returning them to the blood. Okay, this could be through the transcellular or paracellular route, huh? As it being absorbed. Sodium is the key. Where sodium goes, water follows. So in this case, if sodium enters to be absorbed, some water can also be reabsorbed. Huh? Another item here is that the the sodium will end up being a factor in the epithelial cells. Huh? You pump out sodium, extracellular fluid is also taken out. So that sodium again is very important in this situation. Negative chloride ions follow the positive sodium, and therefore you end up having antiport in the apical cells that absorb the chloride. Okay, this is tubular reabsorption. Potassium, magnesium, phosphate ions diffuse through the paracellular route, and some of them go through the epithelial cells. Some can also be reabsorbed through the paracellular route in the proximal convoluted tubule. So in this picture here, reabsorption in the proximal involves the solvent drag, which brings items back to the peritubular capillaries, or the peritubular capillaries receiving back what's in the urinary tubule. Okay. Now, the nitrogenous waste, which is part of the urea, is reabsorbed together with uric acid. Now, if it is not maybe to a small percentage, but otherwise it's actually pushed out through the urine. Now, the peritubular capillaries, by the way, huh? So let me go to this picture real quick. Okay. Okay, again, if it's reabsorbed, that means it's coming out of this tubule and then into the peritubular capillaries. These peritubular capillaries, the name itself, peritubular, means around the tubules, pertaining to around the tubules. If you saw the picture, some plates back where there's a medullary nephron, cortical nephrons, and you see all this uh, lining inside, then this is how the items are reabsorbed, huh? And let me see if I could get a picture back real quick. Uh, Almost. There you go. There you go. So you see, class, huh? This is the glomerulus. Then it goes to the proximal convoluted tubule. Then it goes down to the descending loop, the ascending loop, and then you have the actual proximal convoluted tubule connecting it to the collecting duct. So this means that when you say it's being reabsorbed, it will come from the tubes and reabsorb back in that capillary area here. The smaller blood vessels make up for the capillary. And so therefore, if it's to be reabsorbed, this peritubular capillaries around the tubules, peritubular, actually is there to take whatever is being brought back to the stem. So as it exits through the tubules to be reabsorbed, it will then enter these peritubular these capillaries here, and then this will end up joining the vein, huh? Okay, so it's basically helping to control that situation. If it's secreted, that means it's coming from the peritubular capillaries back into the tool. Okay, so when that happens, you're able to secrete items that the body says, actually, I don't need that anymore. So it's able to throw that in and be flushed in the urinary system. Okay, so that's where your peritubular capillaries exist. This is also a lot of peritubular capillaries here, see? Okay, so that's what you mean when you say peritubular capillaries. Let's see if I could swing this back a little bit more. All right, hang on. I'm gonna put the slide back. Okay, moving up. So there's your tubular absorption and secretion. Okay, there's a picture here. I'm trying to look at it. I don't have it in this slide, but it shows it shows how much the reabsorption and the secretion. In your book, in your textbook, you will have a page there. I'm not sure exactly what number for now, but it will show where the maximum reabsorption happens in the proximal convoluted tubule, while the maximum secretion happens in the um, later part, the distal convoluted and the collecting duct. Okay. By the way, like I said before, when you drink medications in order to control blood pressure, it has to work with the kidney. So that said, medications will end up stimulating the kidney, but also it will also be broken down by the kidney. If you take potassium sparing diuretics, it will take effect on the distal convoluted tubule, right? If you have the antidiuretic hormone produced by the pituitary gland, it will also stimulate the distal convoluted tubule and also the collecting duct. So you see, those are items when, right, the distal convoluted tubule is much needed. If you have aldosterone, again, aldosterone works with the distal convoluted tubules, a little bit of the uh, that area. Aldosterone will then make sodium be reabsorbed by the distal convoluted tubule, and if you reabsorb sodium, you will reabsorb water. So that's where the uh, location is being made. This is the distal convoluted tubule. If you secreted ANP, atrial natriuretic peptide, its effect is also going to be at the distal convoluted tubule and collecting duct. But what it will do is it will make the distal convoluted tubule not accept or not pick up anymore uh, any more of that situation. Okay, so that situation involves sodium. So by not taking in sodium, which is always followed by water, you actually are not taking in water. See? So basically, it helped the situation. Okay, that's ANP. ANP lessens the pressure. So the mechanism of ANP is to not absorb sodium, so you don't have water being absorbed by the body. It lessens the pressure. Huh? Remember, the ANP is produced by the heart because it's having too much pressure and too much work for it. Okay, so that's showing you that the medications, the hormones, affect the distal convoluted tubule mostly in the whole of the glomerulus or the nephron. All right, class will take another short break here. Help the recording maintain the signal. Okay, we'll take a break and then we'll come back in a few minutes.